Good morning, and here we are this morning in outer space, demonstrating the ability of the amazing 5x12 matrix to work in confined spaces. And we are in static outer space. And please don't try this in dynamic outer space. Uh, so here we are, and we are doing a circuit analysis here. And we have projected for this demonstration a 3x3 mesh circuit. And I must stipulate once again that we should be able to move from the linear domain into the matrical or the matrix domain or the matrices domain. So here we are with a 3x3 mesh circuit, and we are for mesh A, mesh B, and mesh C with loop current IA, IB, and IC. We could also say mesh 1, mesh 2, and mesh 3. So we have R1 is equal to 10 kilo ohms, and I going like this. We have A, loop IA current going in the anti-clockwise direction here. And it's IA unknown. We have this voltage here, source voltage, 15 volts. And we have here 5 kilo ohms. In mesh 2 here, we have the mesh C. We have plus V3 voltage there, and I going in this direction. IC going in the anti-clockwise direction again. Or that's what, that's clockwise. Yeah, this is clockwise. And this one is also clockwise. So all three currents are going in the clockwise direction. And with their resistance is 10 kilo ohms, and here we have 5 kilo ohms again. So we use a KVL equation for mesh A, B, and C. KVL equation for mesh A, B, and C. And we have mesh A, V1 plus V2 equals 15 volts. Mesh B, V4 plus V5 equals 15 volts, which is the source voltage. 15 volts here. And mesh C, V2 plus V3 is equal to V4. Well, in confined outer space here, and this is the ability of the amazing 5x12 matrix to work within confined spaces. In New Jersey, we show in a cargo bus, and in Atlanta, we did it in a cargo bus, again, a passenger bus. And now we are in even a smaller space, confined space, and applying the amazing 5x12 matrix. And this is a breakdown components with a 3x3 matrix. So you have I1 is equal to now I1 equal to minus IA, and V1 is equal to 10 kilo ohms times I1, and is equal to minus 10 kilo ohms times IA. And I2 is equal to IC minus IA, and V2 equal to 15 kilo ohms times I2 equal to 5 kilo ohms into IC minus IA. And so on and so forth. We come down to I5 equal to IB, and V5 is equal to 10 kilo ohms times I5, and equal to 10 kilo ohm times I5. I'm making my 5 look like a 3 here, so this could have been a 3. Let's go back to the circuitry and see what it is. So mesh A, what we have here is 10 kilo ohm plus 5 kilo ohms times IA minus 5 kilo ohms is equal to minus V source. And mesh B, 0 times IA plus 10 kilo ohms plus 5 kilo ohms times IB minus 5 kilo ohms is equal to V source I. And that mesh C minus 5 kilo ohms IA times IA minus 5 kilo ohms times IB plus 5 kilo ohms plus 10 kilo ohms plus 5 kilo ohms is equal to 0. And of course, these are in the bracket here. And so we translate the linear standard now into the matrix form. And here we have, we will show it more explicitly, the matrix form here now. And we have now R11, R12, R13, R21, R22, R23, R31, R32, and R33. And correspondingly, the resistance and is over here shown 10 kilo ohms plus 5 kilo ohms for R11, R12 is 0, and R13 is minus 5 kilo ohms, and R21 is 0, R22 5 kilo ohms plus 10 kilo ohms, and R23 is equal to minus 5 kilo ohms. R31 is equal to minus 5 kilo ohms, R32 is equal to minus 5 kilo ohms, and R33 is equal to 5 kilo ohms plus, let's see if we could show it more, 5 kilo ohms plus 10 kilo ohms plus 5 kilo ohms, that will be equal to 15 kilo ohms. And it will be no times IA, IB, and IC coming down in row 1, row 2, and row 3 here. And that's equal now to the source voltage is now minus 15 and 15 and 0. And so we solve IA, IB, and IC. And we get now minus 1.0 milliamps, 1.0 milliamps, and 0 milliamps. We could also use a graphing calculator or matrix software and do the solving. And we calculate the device